Hi there, this is Math 7, Unit 8, Lesson 14, Sampling in a Fair Way. So when we talk about a fair way, what we're going to be focused on today is making things, well, fair, right? And the way we talk about that in statistics world is we talk about something that has a bias, okay? A bias means that it's not fair. So if something that has a bias is not fair. And we want to have things that are fair, so we want situations that don't have any bias in it. Okay? And so bias is like meaning that you have, like for example, you might say someone is a favorite. If you have favorites, that's having a bias. So if you do a sampling, you do a survey, and you want to like have it come out a certain way because you like a certain thing better than another, that's having a bias. Okay? So let's say, for example, you liked chocolate chip cookies, and you wanted to see which kind of cookies people like best. So you gave them, 4 chocolate chip cookies to choose from, and then you created another cookie that was completely burnt and made out of pumpkin and maybe some squash and some leftover horseradish. Okay, and you said, which one is your favorite one? Well, they're going to keep picking the chocolate chip because this one is disgusting. Okay, unless you like that, I don't really know. Probably you might. So that's like a bias. That's not really a fair thing, is it? So your count's going to be off. But anyways, maybe not the best example. We'll get into it. So here's a survey. So the survey was taken at a movie theater to estimate the average age of moviegoers. So imagine going to the movies, which are currently all closed, going to the movies to find out what is the average age of people at the movies. This is a dot plot showing the ages of the first 20 people surveyed. So they asked 20 people what their ages are. We have a 4-year-old, 5-year-old, 6, 7, some 8s, a bunch of 9-year-olds, a few 10s, and an 11-year-old. We have a whole lot of little kids here and no one bigger than 11, right? So we're between 11 and 4 years old. So what kind of questions do you have about the data from the survey? What are some things you kind of wonder about and you go, that seems interesting, or things you think about? I guess for me, I'm looking and wondering, why are the people so young is one thing I'm wondering. I mean, everybody's young. Everyone they asked the first 20 people and they were all 4 to 11 years old. Maybe I'm also wondering something like, where are the adults, right? That you asked 20 people and didn't see a single adult? That seems a little odd, right? Okay, and maybe I'm wondering what movie theater you're going to, what movie or movie theater you're going to that only has little kids at it. That just seems weird too. Okay, so the data though is a little bit off, right? Do you think this really represents all the people at the movies? Probably not. Most likely when you go to the movie theater, you're not running into mostly 4-year-olds to 11-year-olds at the movie theater. If you are, you're probably watching, maybe a Disney movie, or you're watching Frozen 2 once again. I don't know. So what assumptions would you make based upon these results, which you've already started to make here? Assumptions is, what are some things you would assume about the movie theater if you just looked at that? What are some things you'd think about? Well, I would think that maybe you're at a little kid movie, right? Maybe a rated G for just little kids. The next Toy Story is out again. Like I said, Frozen 2, or something that's really fun for little kids is there, and you're there. Maybe it's a little kid birthday party, and you just happen to get the whole group as they walked into the movie theater at that same time. Okay? These are things you could maybe assume or make some assumptions based upon that data right there. Doesn't mean it's accurate or not, it's just what do you think based upon what you see. Okay, so the next thing we're going to do is we're going to compare methods for selecting samples. Okay, we're going to take turns with your partner reading each option out loud. For the situation we want to discuss, would the different methods for selecting a sample lead to different conclusions about the population? Again, remember a sample is a part of the population, is all of everything. So if you're doing a sample and the way you select your sample, does the way you select your sample impact how you view the whole population, right? If this is my sample of moviegoers, my assumption is everyone at the movies is a little kid. Right? That's what it looks like. I'm not right, but that's what it looks like. So sometimes the different methods we choose have an impact on how we could view and have conclusions about that population. We can talk also about the benefits of each method and maybe look at what each one might overlook. By doing it a certain way, what are you missing? Which of the methods listed would be the most likely to produce samples that are representative? So you want to figure out what's the best way to get representative sampling. Okay, and then can you think of a better way? Let's take a look at a few examples here. It says that Lynn is running in an election to be president of 7th grade. So here's Lynn trying to become the president of 7th grade. That's her goal with the class election. She wants to predict her chances of winning. So here are her ideas for surveying a sample of the students who will be voting. So just a part of the whole. What if she was to ask everyone on her basketball team who they're voting for? All right. So is that a good idea? Is that going to be biased? Is that going to be representative of the whole school? Well, let's think why it could or may not be. First of all, I noticed that these are people on the basketball team. Okay, so maybe the basketball team likes, maybe these are sports kind of focused people, and she's a sports person, so they like that. But maybe not everyone's into sports. Also notice this is her basketball team. Because it's her basketball team, these are probably her friends, right? So most likely her friends are going to say, yeah, I'll vote for you to be president there. But this is just one team. A basketball team may only have a total of maybe 10 or 12 players. So you're asking 10 or 12 people that are already your friends that like the same things you like, who they're going to vote for. That sampling might be something like, 8 vote for you yes, and 2 vote no. I mean, I'm just making that up there. And you might think, yes, I'm going to win. But you're just asking your friends. So that's probably not the best sample that you could use in order to see if you might win as president. How about if you ask every third girl waiting in the lunch line who they are voting for? Now, waiting in the lunch line means you do have some people who are likely to tell you yes or no, right? That's good there. And every third, that's a pretty good idea there, because now it's not just, it's a little more random, so I like that part. But just asking the girls, that seems to be a little problematic. If you're only asking the girls on the lunch line who they're going to vote for, does that represent all of the students who will be voting? No, because I'm guessing the boys are going to vote too. So you might find out, yes, the girls really like you, but there are boys at school too. So what about the boys? They're not a part of your sample, so that would not be representative. Again, the goal is to be representative. That's the goal. What if you ask the first 15 students to arrive at school one morning who they are voting for? Okay, so it's the first 15. You don't have any control of that, so that's a little bit random there. Random is good. Okay, you have 15, so you have kind of a small sample size. Okay, you might want a little bit more of a number to ask to make sure it's legitimate or not. The fact that these are people there that are first ones there in the morning, they're maybe a little bit more excited to be there, or I don't know, maybe they got dropped off, who knows. But overall, I would say this is the best representation for the student body. It makes the most sense. It's a good random sampling of just all the kids at school. First 15 could be boys or girls, they could be 7th grade, 8th grade, hard to say, but it's more random, so it's more representative. Looking at number 2, what do we see here? It says a nutritionist wants to collect data on how much caffeine the average American drinks per day. So we're looking at caffeine per day. We're talking about how much caffeine people drink each day. So here are the ideas for how to get a sample. Again, sample is part of the whole. We really want to know all Americans, about how much caffeine do all Americans have every day. So what if she asked the first 20 adults who arrive at a grocery store after 10 a.m. about the average amount of caffeine they consume each day? Well, that sounds pretty good so far. 20 adults, well, 20 adults, we are excluding young people, right? So young people are not included here. So that makes it not perfect. It's okay. Adults is pretty good, but you aren't including children or young people who probably also have caffeine, which of course, you might think about caffeine coming in the form of coffee if you're an adult, but maybe also soda, especially for young kids and adults as well. All right, you're at a grocery store, so that's okay there. 10 a.m., well, maybe 10 a.m. is not the time of people that drink a lot of caffeine at the grocery store, okay? I know for me, I get a cup of coffee, and that's the first thing in the morning. I come into my office, my work, and I pour the water in the machine, and I put in my little K-cup, and out comes my cup of coffee in my nice Disneyland mug. So, How does that work? It works out pretty well for me. Okay, so but at 10 a.m., I'm not at the grocery store. I've already had my coffee and I'm working at work. Hard to say. So this one is a maybe. I think it might be okay. It's not perfect, but it's maybe pretty good. Let's look at choice B. Every 30 minutes, I like that idea, every 30 minutes, you ask the first adult who comes into a coffee shop. Well, I like the every 30 minutes. That was nice and random. I liked asking the first adult, although, again, kind of like the other person, you're forgetting about the young people, so same problem there. But now you're at a coffee shop? Well, goodness, everyone in the coffee shop is having caffeine. So if you're collecting data on how much caffeine the average American drinks per day, you're asking people that are going to the coffee shop to get more caffeine. So you're asking people who are definitely going to be biased, right? There's going to be a bias there. Whatever they say is going to make it sound like there's more caffeine drinkers in the world than there are non-caffeine drinkers because you're in a coffee shop. That's kind of how that works out. All right. That's it for that one. Let's look at 14.3 real quick. Okay, 14.3 is a great little experiment for you to do. I'm not going to do it here on the video today because what it wants you to do is it wants you to draw some straws from a bag and then keep the record of how long those straws are. Okay, you're going to record the lengths there, and then once you get the lengths, you'll find the mean, right, of the first one, add them up and divide by 1, 2, 3, 4, 5, right? So you find the sum and divide it by 5. And then the second one, you find the sum and divide it by 5. Then you want to see if your two estimates were the same. Again, it's the same experiment each time with these straws in the bag. What does it come out to? Did the mean length of all the straws change? Probably it might change a little bit, right? So why would it change? Why would you find a change there? It's a great experiment, again. And the actual mean length of all the straws in the bag is 2.37. So what's going to happen is you're going to do this experiment and you're going to get a mean that's maybe something like 3.8 or all the way up to maybe like 4.4. You're going to get a pretty good sized mean there when you do this based upon the different straw lengths that are in your bag. And now what we're telling you now is though the actual mean is 2.37. So how does your estimates compare? Well, if I'm telling you your estimates are going to be about that, but they actually should be about that, it tells us that our estimates are too high, aren't they? Why are they too high? You gotta think about, we're talking about having a biased sampling. So what could be happening with all the straws that makes our mean higher than what it really should be? Makes our sampling tell us that the length of the straws is longer than it actually should be. Okay? And then if you repeat the same process again, but you selected a larger sample, such as 10 or 20, would your estimate be more accurate? And then again, based upon what we're going to see, it's kind of a maybe. It might be a little bit, but it's still going to be a little bit off. Now the reason for that I'll get to in the next thing, because when we look at activity 4 tells us that there were 35 straws in the bag. Now of those 35 straws, there were 6 different lengths. So you have the length, and you have the number of straws. I'm going to make a little table here for you to tell you what's actually in that bag now that that part's over and we're not going to do it. You had some that were a straw that were half an inch long. There were actually 6 of those. You had ones that were 1 inch long, and there were 6 of those. We had 2-inch long straws, and there were 8 of those. We had 3-inch long, there were 6 of those. You had 4-inch long, and there were 5 of those. And then we had the 5-inch long ones, and there were 4 of those, for a total of 35 straw lengths. Okay, so there's 35 of them all together. That was what's actually in the bag. So what happens though, and look at this here, what are you going to most likely draw out? Think about it. You have some that are this long, half an inch in a bag. Yeah, there's 6 of them, but they're pretty tiny. If you reach your hand in a bag to pull out a straw that's this long, are you going to select that one? Or are you more likely to select the one that's 5 inches long by putting your hand randomly in a bag and just pulling out the first one you grab? And this one here is actually probably more like 4. So we did a 5-inch, you'd probably go more like to here, right? I would say you're probably going to grab this one over that one because it's just much, much larger. That's why your averages, your means, were so much larger than what they should have been. So let's now move to this next activity. Suppose you put the straws in order from shortest to longest, and then assign each straw a number from 1 to 35. For each of these methods, decide whether it be a fair way to select a sample of 5 straws. So the example here is like you're having a ½ inch, right? And that's number 1. Another ½ inch is 2. Another ½ inch is 3. Another ½ inch is 4. Another ½ inch is 5. Another ½ inch is 6. And then we go to our 1 inch ones. 1 inch is 7. 1 inch is 8. 1 inch is 9, right? And so on until we get all the way up to our very last one, which is 5 inches. You're putting them in order from the smallest straw to longest straw for all 135. Now we're going to get a sample of 5 straws. So what if you select the straws numbered 1 through 5? Is that going to be representative? Again, that's the idea. Representative. Does it represent all, right? Does it represent all the straws fairly? Fairly. No bias is what we're trying to find out. That's what we're asking. So if I just pick these 5, in this case here, ½ inch straws, does that represent all the straws? Well, I'm guessing you're going to say and agree with me here, no, it does not. It is not representative, okay? Is that a fair way? No, it is not fair. It's not a fair way, okay? Because these are what? The shortest straws of all 35. So no, that's a terrible way of doing it. Now what if you write the numbers 1 to 35, again how many straws are there? 35, on pieces of paper that are all the same size. Same size means they have the same chance of being drawn. You put the papers in the bag. Without looking, you select 5 papers from the bag, and you use the straws with those numbers for your sample size. So you randomly pick up and you say, I drew number 7, I drew number 12, I drew 23, I drew 3, and I drew 31. Okay? And you have those as your straw lengths or numbers. Then you go back to the list and go, okay, I'll take this one, I'll take this one, I'll take, and so on. Is that a more fair way of finding a sample that represents all the straws in the bag? We would probably say yes. Why? It's much more random in the way it's done. Everything has an equal chance of being drawn because every piece of paper, whether it's 30 or another number, is the same size. So they all have an equal or a fair chance. Right? Wouldn't you want a fair chance? Okay? If you put your names in a bucket to try to get a prize, but maybe your name is written on a piece of paper this big, but your buddy's on a piece of paper this big, right? I'm going to think that's not very fair. And that's what we have here. This is a good, fair one. Look at number 3. Using the same bag as the previous question, select one paper from the bag, use the number on that bag to select the first straw for your sample, then use the next 4 numbers in order. So for example, if you pick 17, then take 17, 18, 19, 20, 21. Okay, is that going to be a fair way of figuring out kind of the average straw length? Again, well, if you like that idea, let's pretend you did. If you did 17, then you picked 17 and had to get 18, 19, 20, and 21. If that's a good sample, what happens if you pick 2? Then you have 3, 4, 5, and 6. And those were all ½ inchers, weren't they? That was only ½ inch long. My average in that case is going to be ½ inch. How about here? This average is going to be probably more like 3 inches. Okay, perhaps. There's a big difference there. So this is not a good way either. It's not random, and the numbers that you're selecting are just too close together for this data set there. Doesn't make sense. And finally, number 4, you create a spinner with 35 sections that are all the same size. I like that again. Why do I like the same size? Because it has the same chance, right? Or, dealing with math here, same probability of being spun. You spin that spinner, and if it lands on one of them, it's a winner, okay? Whatever you spin, those 5 times, that's the straw you pick. And again, this is all referring back to how the straws are organized and laid out in size from smallest to greatest. Okay? So that's really the idea, looking for what bias is, making sure that things have a fair chance of actually taking place so that your sample actually matches your population. That's the whole goal. So, a sample is selected at random from a population. That's the thing to remember. A sample is selected at random from a population. if it has an equal chance of being selected as every other sample the same size. So, why is it we say it's at random? It only happens at random, selected at random, if it has an equal chance. Equal chance is important. If it doesn't have an equal chance, it's really not a random sampling. It's not going to be very good. Okay. Other methods of selecting a sample from a population are likely to be biased. So if it's not going to be fair, it's going to be biased. This means that it's less likely to sample will be representative of the population as a whole. And that's very true there. And finally, when a sample cannot be selected at random, it's important to try to reduce bias as much as possible when selecting the sample. Because again, the goal is with a sample to be able to take a small number, right, and be able to predict or project from there what it would look like in a larger context. Because you don't have the time, the resources to figure out the big part, so use a little part there. Again, think about the blood example from before. If you go to the doctor, you want him to take a sample of your blood, meaning just a part of it. You don't want him to take all your blood. That's going to be too much. But you're hoping that the part that he tests is representative of all the blood in your body. Okay, let's pause there. You can work on your homework and we'll check it together in just a couple minutes. All right, here we go. Math 7, Unit 8, Lesson 14, Sampling in a Fair Way. It says the meat department manager at a grocery store is worried some of the packages of ground beef labeled as having 1 pound of meat may be underfilled. Ooh, not quite a 1 pounder. He's worried about that. He decides to take a sample of 5 packages from a shipment containing 100 packages. So that he wants to take a look at 5 out of 100 of them. Okay. The packages were numbered as they were put in the box. So each one has a different number between 1 and 100. Okay, so they were just numbered as they're put in there. How can he select a fair sample of 5 packages? Right? You know, if you took them right off the top, if you said, okay, here's the case of meat, and you just took them right off the top and just grabbed the first 5 you saw, because they're put in order, that would mean the last 5 put in, it's not really random at that point because they're put in there in a certain order the way they're made. I want to make sure that the whole box is okay, right? I want to check it out, so I want a good random sampling. So one way you might do is you might write down some numbers. Might write the numbers 1 to 100, okay, and then pick 5. So you pick, let's say you pick numbers again 7, 27, 38, 59, and 83. Then you take those numbers there and you select the beef with that number and check the weight. That way, whatever numbers you draw, you're going to get those random packages of beef to check those weights. This is completely random. There's no bias whatsoever. So that would be a great way of doing that there. Are there other ways? Of course there are. That's just one way there. Okay, number 2. Select all the reasons why random samples are preferred over other methods of getting a sample. Why do we like random samples? A. If you select a random sample, you can determine how many people you want in the sample. That doesn't make any sense. You can determine how many people want a sample before you do a sample. So that doesn't make any sense. A random sample is always the easiest way to select a sample from a population. This word here, always the easiest, kind of gives it away. Like, I don't think so. Always, probably not always. Sometimes, maybe, but always, no. A random sample is likely to give you a sample that is representative of the population. Yeah, that's the whole idea. It's likely to give you a sample that is representative of the population. That's the whole point. A random sample is a fair way to select a sample. We hope it's fair because each person's population has an equal chance. We like fair, we like representative, we like equal chance. Those are all good things. If you use a random sample, the sample mean will always be the same as the population mean. Well, not always. Sometimes your sample is not perfect, so it can't always be. That always word again gives away like, nah, I don't think so. Number 3, Jada is using a computer's random number generator to produce 6 random numbers. So it's a computer. The computer is making a random number. Good job, computers. They're pretty good at this, right? Between 1 and 100. So she can use a random sample. The computer gives you the numbers 1, 2, 3, 4, 5, and 6. Should she use those numbers? Or have the computer generate a new set of random numbers? Well, it's a great question. For you and I, we would go, man, that looks like it wasn't mixed up pretty well, right? Have you ever seen it before where people put tickets in a box, right? And they're going to draw out the winner, but they only put the tickets, they don't really shuffle them very well, and the guy reaches in with his hand and takes the one right on top, and like, that's the last one that got put in there. I came early, mine's in the bottom, right? It looks a little bit like that, doesn't it? But if you trust the computer is working, then those are random numbers. You could have random numbers that look like there's an order to it. That could happen. The odds of it happening are very, very small, but it could happen. So would you keep those? You probably could keep them. Now, if you weren't sure and weren't confident about that, you could try running it again and just test it one more time. But that'd be up to you. But the answer really would be yes, you could use those numbers, she could use those numbers, and it would be okay. Doesn't look okay, but it is okay because we're trusting the computer is not broken. Number 4. A group of 100 people is divided into 5 groups of 20 people in each. Okay, so we have 100 people divided into 5 groups of 20 people each. So we have 20, 20, 20, 20, and 20. Those are our groups. We have 5 groups of 20, right? One person's name is chosen, and everyone in the group wins a prize. So there's 20 names, right? 20 names in a list. Those are my names in a list, and those are great. And you pick that name there. Winner! Everybody gets a prize. Awesome. Noah simulates this situation by writing 100 different names on papers and then putting them in a bag. That's a lot of names. Did I write 100 names? No, I did not. That would take forever. Kieran suggests that there's a way to do it with fewer paper slips. Explain a method that would simulate the situation with fewer than 100 slips of paper. So he's taking all the names and writing them down. Okay? What if we assigned each group of 20, a number or a letter? Okay? And we say, this is group A, group B, group C, group D, or group E. Or maybe you assign a group 1, 2, 3, 4, and 5. Alright? And then you put those numbers or letters in a bag, and you randomly pick one. You pick number 3. Yay! Well, who wins? All those people again. So what's the chance of winning when I look at those numbers 1 through 5? I have a 1 out of 5 chance. What's the chance of winning here if I pick one name out of 100? Well, it's not one name out of 100 because actually 20 people get the prize. So actually 20 people can win out of 100 even though I'm picking one name. Well, 20 out of 100, again, as a probability is 0.20. And 1/5 as a probability is 0.20, meaning they're exactly the same. They're the same groups, just a different way of representing them. Instead of looking at one part of the 20 for the name, I'm doing one part out of 5. All right, flipping it over to the next page. Data collected from a survey of American teenagers aged 13 to 17 was used to estimate, so teenagers 13 to 17, was used to estimate that 29% of teens believe in ghosts. The estimate was based on data from 510 American teenagers. What is the population that people carrying out the survey were interested in? So what is the all they were wondering about? Who is the all? Were they wondering about all people in the United States? Well, if they were, why did they only ask teenagers? If they were, that'd be a terrible sampling, right? So if they weren't worrying about all the people. Were they worried about 510 teens? No, this is a sample. So 510 is a sample, not the all. All American teens who between 13 and 17. Well, I like the word all there. I like that we're focused on the teenagers, and 13-17 is who the group is. That makes sense. Were they focused on 29% of teens who surveyed? Nope, that was just the probability, so no as well. Okay, number 6. A computer simulates flipping a coin 100 times, then counts the longest string of heads in a row. You got 8 in a row, 6 in a row, 5 in a row, 11 in a row, 13 in a row for heads in a row. Way to go. Based on these results, so based on what you see right there, estimate the probability that there will be at least 15 heads in a row. Well, looking here, do we get 15 heads in a row at all? No. So we could say that the probability is 0. But could it happen? It could. but the likelihood of it happening is probably pretty small. So I would say it's going to be anywhere between 0 and 1/5 of a chance of happening. So even that, it's going to be a little bit hard. Could it? It could. Now, could it happen twice? Probably not. So at best, I would say it has a 1 in 5 chance of happening. But even that, I don't think it's even possible. That's it for today. Have a great day, and we will see you next time.